Alright, today we're going to take a look at area within a polar curve. Now, if you want to look the proof for the form that we're going to be using today, go to part 2. I'm going to have a little bit of a proof there for you. It might help you out. So, we're given a polar curve. Radius is in terms of theta, where the angle goes from A to B. Now, to get the area, it's this formula right here. 1/2 of the integral from alpha to beta. Those are angles of r squared d theta. And I said in part 2, I'll explain how we get that formula. But it's pretty easy to prove and understand. We want to find the area bounded by this graph. Now, we know this is a cardioid. Some people think, oh, I know it's a cardioid because A is equal to B. I always have a hard time remembering that one. So what I tend to do is I simply say, okay, the smallest this is ever going to be is -2, and that becomes 2 minus 2, which is 0. It touches the pole, which makes it a cardioid. But using your tables, we can get 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if I graph this, at 0 we get 2, so it's 0 radians, we're at 2. At pi over 2, that's going to become 2 plus 2, which is 4. So I'm facing pi over 2, we're up at 4 units. At pi, we're back to 2. And 3 pi over 2, this becomes 0. This right here is what tells me it's a cardioid, because my radius goes back to 0 here. And at 2 pi puts me back at the beginning. There's my 2 pi. So here's pi, 3 pi over 2. So when I graph it, I'm starting at 0, 2, and I go around the function. Okay, because polars are based on circles. We're going to go around. Now, once I get to this point, I'm not going to go flat across. It's a cardioid. So we dimple down a little bit, touch the pole, and we get what some people call a butt. So you can say math has mooned us. So when I want to find the area of this, I'm going to use a formula. Now before we do that, like I said, if you go to part 2, what you got to think about area, what you got to think about this is like it's a windshield wiper. Okay, I have a windshield wiper, a magical windshield wiper. And like right there. And what's going to happen is I'm going to rotate this windshield wiper from the pole, and I'm going to go around. And as I'm going around the pole, I'm filling in the area of our cardioid, like so. So when we set this up, and this is the most important thing, because when we do function rectangular coordinates, we always go from left to right. But for polars, we're going to go around. We're going to swing around. And as we swing around, we're going to fill in our cardioid here. So when you do your area formula, it's going to be 1/2, our rule says, square this 2 plus 2 sine theta squared d theta. When we do the domain, you got to think, well, if I start at 2 pi and I rotate all the way around, I swing it all the way around, I have to go all the way around the circle. So starting at 0, I end up at 2 pi. And that's going to give me the area around the entire cardioid, filling it in as we rotate our magical windshield wiper around. So kind of a hint for us, if the function's a limaçon, which this one is, and we want to find the area of a whole limaçon, we tend to let theta go from 0 to 2 pi. And now I'm going to integrate this. Before I can do that, though, I do have to expand it. 0 to 2 pi. I get 4 plus 8 sine theta plus 4 sine squared theta, d theta. Now, I don't like sine squared theta. I do have to rewrite that. That's one of our techniques. We're going to get 1 minus cosine 2 theta over 2. So when I expand this again, I get 4 plus 8 sine theta plus 4, and this becomes 1/2 plus 1/2, minus 1/2 cosine 2 theta, d theta. Now I'm going to distribute here, 0 to 2 pi, and when I distribute, I'm going to combine like terms. This becomes 2, this becomes a 1, so I'm going to get 3 plus 4 sine theta minus, this becomes 2, times it by another half is 1, cosine 2 theta d theta. At this point, I can now integrate 0 to 2 pi. I get 3 theta minus 4 cosine theta minus, be careful, 1/2 the sine of 2 theta. So there's my antiderivative, but now I got to apply the FTC minus, plug in the 2 pi, I get 6 pi minus 4. Cosine of 2 pi is 1. Sine of 4 pi is 0. Plugging in the 0, that's just 0 minus 4 times 1 minus, again, 0. And when I wind up with, the 4 pi's cancel. I get 6 pi for my area. So the next we're going to take a look at is a flower. Now the flower is a little harder to graph. So what I'm going to do is, this is a petal. This is a 3 petal rose. So if she loves me, not she loves me. This is a good one. We like this one. If I want to sketch it, I'm only going to sketch 1 petal. Now to help sketch a rose, these are a little bit harder to do, I think, to graph. So I've learned another way somebody once taught me. Says what we're going to do is we're going to find out where the radius is 0. So if I set my radius of my function equal to 0, and we'll explain why we do this in just a moment, we get the sine of 3 theta equals 0. 3 theta equals 0 pi 3 pi. Because it's 3, I go around it twice. 3 times. 3 pi, 4 pi, 5 pi, 6 pi. And if I solve for theta, we get 0 pi over 3 pi, 4 pi over 3, 5 pi over 3, and 2 pi. Now the reason I set this up, now this is not how we graph a rose normally, but it will give us an idea. If I go between 0 and 3, remember, this says I'm starting at 0. Like if I were to graph this theta and r, if I started at 0, my radius is 0. So when I'm facing 0, I'm at 0. This says if I'm at pi over 3, my radius is also going to be 0. So if I'm at facing pi over 3, I'm back at 0. Well, think about it. I'm going between an angle of 0 and pi over 3. Both end at 0. Well, what has to happen in the meantime? It has to go out and come back. So that gives me one of my petals, which is what I wanted. So when I want to set up my area, I'm going to type it in 1/2 r squared 2 sine 3 theta squared d theta. Now, what's my domain going to be? Well, for one petal, my one petal, I started at 0 radians, yep, and I ended at pi over 3 radians. I started and ended at 0. So between each two of these, I get a petal. And if you notice, 3 theta, remember 3 petals? You always go around right here, I go around the circle 3 times. 1 petal, 2 petal, 3 petals. So to get my area, I'm going to pick any two of those. 0 to pi over 3 is the easiest one. I could have done this one. 1/2 pi to 4 pi over 3. 2 sine 3 theta squared d theta. Or, heck, if you want to be really fancy, remember, I can do any two of them. I could have picked 1/2. I could have picked pi over 3 to pi even. And that's kind of a weird one when you want to think about it, because what this is doing is taking half of this petal, so it's going to take like half of this petal and then plus half of my other petal. So it's going to be like 2 halves of a petal is what this one's going to give me. But 2 halves do make a whole. And they'll all give you the same answer. And you can type those in your calculator to verify it. And if you really want to be fancy, you can do this. I can go from 1/2, ready? 1/2, 2 sine 3 theta squared d theta. I could go from 0 to pi over 6, because between 0 and pi over 3 lies pi over 6. That's where the function is going to be at its maximum. But it's only going to give me half of my petal, so I just multiply that by 2 to get the whole petal. So a lot of ways you can answer these, and you can type them in your calculator, see if you get all the same answer here. Tough one right there. This is the easiest. So if you don't like any of this, erase it, erase, erase, and just look at that one. So now let's take a look at another one. This is a 4-petal rose. On a 4-petal rose, I do the same thing. I want to find out where r is 0. So that's going to give me cosine 2 theta equals 0. Now cosine's going to be a little bit different, we'll see. Where's cosine 0? Pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, excuse me, and 7 pi over 2. Now I'm also going to include negative pi over 2. We'll talk about that in just a moment. So if I plug it in, that means solve for theta, I get negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4. Now again, when I do my area, let me turn on my light. When we do the area, we could pick any two of those. Any two consecutive ones will work. Whoops, got my 1/2. Any two will work. Now, the AP is going to want this one. If this is a multiple choice and it's cosine, they're going to pick the negative pi over 4 to pi over 4. So I'm going to use that one just because. But let's take a look at why. It's when we graph it. Because when we graph this, theta and r, if I let r be 0, cosine of 0 is 1. So I'm out at 4. 1, 2, 3, 4. So I'm out over here. When is it 0? At pi over 4. So at pi over 4, I go to 0. So where sine starts at 0 and goes back to 0, cosine does not start at 0. But it kind of makes sense. Remember what the sine curve looks like? Starts at 0 and goes up. But cosine starts top and goes down. So cosine doesn't start at 0. It starts outside. And we can see that right here. So why do they choose negative pi over 4 to pi over 4? Well, from negative pi over 4, ready? Right down here. Negative pi over 4, my value is at 0. So if I go from negative pi over 4 to pi over 4, I'm starting at 0, going out, and then coming back. I get my 1 petal. That's why they like to choose the negative pi over 4s. So for cosine, use negative pi over 4 to pi over 4. Depending, I mean, it could be like, depending on where it is. So you want to use the negatives. And you can check this answer on the calculator, type that in, and get your answer there. All right, hope you guys had fun. I'll see you guys later. Bye-bye.